Mathematics is built on prime numbers. We treat them like atoms, the indivisible building blocks that form the basis of all other numbers. But when you place them on a standard one-dimensional number line, their placement looks like static. They are scattered without any obvious rhythm or reason. The gap between one prime and the next is notoriously erratic. Sometimes they appear back-to-back as twin primes, like 11 and 13. Other times you find yourself staring across massive numerical deserts with no primes in sight. This schematic identifies the stall point, the exact moment where our current analytic proofs fail. Relying on a linear timeline forces us to treat prime gaps as chaotic noise, which is exactly why some of the hardest problems in mathematics remain unsolved. But what if prime numbers possess a strict logical architecture that is simply invisible on a straight line? What if we have been examining the evidence in the wrong dimension? To test that hypothesis, we have to take primes out of that narrow one-dimensional hallway and drop them into an expansive two-dimensional space called the complex polar plane. By abandoning the number line entirely, we can use geometric rotation to see if a hidden structure finally emerges. The complex polar plane functions like a radar screen. Instead of plotting points up or down on an x and y axis, we map them based on two variables, their distance from the center and their rotational angle. Our first rule controls the distance, or magnitude. Instead of placing a prime based on its actual value, we position it based on the inverse of the gap between it and the preceding prime. This inverse calculation creates a physical pull. Massive gaps move the points toward the center of the grid, while frequent tiny gaps push them outward toward the edge. Next, we have to establish the rotational angle. If we use standard whole numbers to dictate the spin, the points immediately clump together into predictable spokes that reveal nothing about the underlying sequence. This slide details the solution. To determine the angle, we use the golden ratio as a strict multiplier. Because this ratio is an irrational number, it ensures that each point sits on a unique part of the circle. This forces the primes to spread perfectly evenly around the circle, creating a nonlinear spiral that avoids any artificial clustering. Combining the gravity of the inverse gap with the spin of the golden ratio, we successfully translate the prime sequence into a 2D geometric space. As the spiral forms, the framework introduces a final architectural rule that elevates the primes beyond 2 dimensions. This growth scale identifies specific milestones called Fibonacci primes. At 2, 3, 5, and 13, the system literally shifts its underlying algebraic base. Every time the algorithm hits one of these milestones, the math scales up. A one-dimensional dot evolves into a two-dimensional plane, which eventually folds into a multi-dimensional cube. When we apply all 3 rules simultaneously, we can observe the geometric result, a structured point cloud that replaces the random chaos of the number line. As this quadrant map shows, we get a dense central disk packed with high-frequency twin primes, surrounded by a sparse outer ring. This ring represents the expansion zones of the most massive prime deserts. The MCPPV framework demonstrates that when mapped as reciprocal gaps and rotational vectors, the prime sequence follows a highly structured, consistent geometric organization. This visualization tracks the transition from discrete points into continuous spectral geometry. Those clusters we mapped in polar space now align with the oscillations of a harmonic signal. This shift provides the basis for the shortcut hypothesis. If primes act as harmonic waves in a geometric space, we may have a new way to predict where massive primes will emerge. We no longer need to exhaustively count up an infinite timeline. Instead, coordinate geometry identifies the exact intersections where primes are mathematically required. This research describes primes as the minimal mathematical skeleton, the immutable structural anchors that allow routing geometry to converge and stabilize the entire universe of numbers. What appeared to be chaos on the number line was actually an illusion of our perspective. In the right dimension, prime numbers are revealed as the ultimate geometric architecture of nature.